Hey guys, welcome to video 66. Today we're going to be talking about the cathode follower, and as you can probably guess, it's very similar in function to an emitter follower or source follower using BJTs or FETs. Typically, cathode followers are used as buffers. That is, they are used to couple relatively low impedance loads to a high impedance source. The first thing that you probably think of if you visualize a cathode follower is this circuit shown over here on the left. And for various reasons, this is not a good practical circuit, but it is convenient for deriving some equations. So we'll start by looking at this. And a couple of the major characteristics are shown here. The voltage gain is less than 1. Its input resistance is approximately equal to the grid resistance. The output resistance is approximately 1 over GM for the vacuum tube. And the output voltage here, peak to peak, is going to be less than the gate to cathode bias voltage for the vacuum tube. And that's the main problem with this approach, is that the output voltage swing is very, very limited, which makes this circuit impractical. Now, fortunately for us, there is a modification we can make to this biasing arrangement that does make the circuit practical, and it's a really cool circuit in its own right, and we'll get to that in a few minutes. But first off, let me lump together RK and RL into a single effective external AC resistance, R'(L), and we'll be using this to do our large signal AC analysis and construct the AC load line for the circuit. If we come over here and we look at the small signal representation for our circuit, I'm using the voltage controlled current source representation for the tube, and as it's drawn here, it's a little bit hard to visualize, but little r sub p, the dynamic plate resistance, is actually directly in parallel with R'(L). So if I redraw the circuit to emphasize that, we can see it very clearly. And I'm going to lump all of these resistors together into a single effective cathode resistor, R'K, and that's little rp in parallel with R'(L), which is Rk in parallel with RL. We'll be using this in the derivation of the voltage gain for the circuit. Now, normally at this point, I would go ahead and fill a few pages with algebra to derive all the small signal relationships, but I thought this time I'll do things a little differently. I'll hold that off until the end, and I'm just going to present the equations in their final forms right now. So let's come over here and start with voltage gain, and as we know, it's always going to be less than 1. And this equation should look pretty familiar to you if you went back and looked at our videos on the common source field effect transistor amplifiers. We had an equation that looked just like this. Now, the output resistance is given by this messy looking thing here. Normally I might combine RK in parallel with RP into a single value, but I couldn't think of a good unique name to give it, so I'm just going to leave it in this form. And if we do a little bit of algebra, we could see that this is equivalent to RK in parallel with RP in parallel with 1 over GM. We've seen this previously with field effect transistors in the source follower circuits also. Now finally, if RK and little rp are relatively large compared to 1 over GM, we can approximate the output resistance as being 1 over GM, and very often that's good enough. Now, as I stated earlier, the biasing arrangement we're using here is not really practical, so let's go on over to the next page and take a look at the modification required to make this thing work. So what we've done here is split the cathode resistor into two parts, RK1 and RK2. RK1 is typically going to be about the same value as we'd have used for all the previous circuits we've looked at. It's maybe a few hundred ohms to few thousand ohms, and it's used to establish our grid to cathode bias voltage. VGK is equal to negative IP times RK1. Now RK2 is used to lift the entire circuit above ground, and it's going to be a pretty high value resistor, typically many times larger than RK1, and it's going to have a relatively high voltage drop across it. We're going to choose it typically to set our plate to cathode voltage somewhere around VPP over 2. That's not carved in stone, but generally speaking, you're going to have about half of the supply voltage dropped across the tube and the other half dropped across RK2. Now, if we want to be really precise, the drop from plate to cathode, VPK, is going to be VPP minus a drop across RK1 plus the drop across RK2. But usually the drop on RK1 is only going to be a few volts, so it really isn't going to make much difference. Most of the voltage drop down here is across RK2. Now, the best way to get a handle on how this circuit works is to just sit down and design it, so that's what we're going to do next. So coming over to the circuit, we're going to use a 12AU7 this time, and let's set our supply rail to 250 volts. And let's pick a Q point. We'll shoot for VPK equals VPP over 2, so that's 125 volts. And let's set our plate current for 2.5 milliamps. So we'll locate this Q point, 125 volts and 2.5 milliamps. That would be right here. And to estimate our grid to cathode voltage, well, let's see, it's a little bit past -5, so I'd call that -5.5 volts. So let's estimate VGK is approximately -5.5 volts. And now using this value in IPQ, we can find RK1. R sub K1 is going to equal 5.5 volts divided by 2.5 milliamps, which is 2.2 k ohms. That's a standard value, so that works out perfectly. And now we have to choose RK2. And an equation we could use here is using Ohm's law, RK2 is equal to VPP minus VPKQ minus the drop across RK1, which would be VGK, just using the positive magnitude, divided by IPQ. So that works out to be, working through this, about 120 volts divided by 2.5 milliamps, and that's 48 k ohms, which is pretty close to the standard value. We'll use 47 k ohms, and there we are. So RK1 is 2.2 k ohms and RK2 is going to be 47 k ohms, and that should give us about -5.5 volts for VGK, 125 volts for VPK. And now we can construct the DC load line. And let's start with VPK cutoff. That's going to be 250 volts, so that's right here. The plate saturation current is going to be 2 times IPQ, so 2.5 mils times 2 is 5 milliamps. Here's the second end of our load line, and let's connect these up right here, and there we go. There's our DC load line. And to finish things off DC wise, let me just fill in these voltage drops. We're going to have 5.5 volts dropped across RK1 and about 120 volts dropped across RK2. Now, before we plot the AC load line, there's a couple of things I want to mention. First off, the design approach I've been using has been to pick a Q point and then construct a DC load line around it. If you wanted to, you could first plot your DC load line, then find a suitable Q point on that load line and go from there. Either way works equally well, and maybe in the next design I do, I'll use the alternative approach, but I just wanted to point out that there are different ways to do these things. And another thing I want to mention is that if we look at our circuit over here, notice that our cathode is sitting at a pretty high voltage with respect to ground. In this case, it's at about 125.5 volts with respect to ground. And don't forget that inside the tube down here we've got a heater or filament that is probably at ground potential or very close to it. So we've got a pretty high voltage on our cathode with respect to the heater, and there are limits we have to watch for here. So let me pull up the data sheet for the 12AU7 for a minute here, and if we scroll down to the maximum rating section, come down here, and we've got heater to cathode voltage, and we can have a specification that's heater positive with respect to cathode or heater negative with respect to cathode. In our case, since the heater is at ground potential and our cathode is at about 125 volts, we have a heater negative with respect to cathode, and we have to make sure that we don't exceed 200 volts. What that means is we don't want our cathode voltage to be greater than 200 volts or thereabouts. Now, normally tubes can withstand more than the rated values given here, but just to be safe, you wouldn't want your cathode voltage to be greater than 200 volts. Now, there are things we can do to eliminate that problem. We could raise our heater to a higher voltage, but normally we're not going to have to go to that length to deal with this. We're just going to limit this voltage. But anyway, that's something to be aware of. We have to watch how high the voltage gets on our cathode with respect to the heater, and in this case we don't want to exceed 200 volts. Alright, let me close the data sheet here, and I'm going to clean up my workspace, and the next thing we're going to do is construct our AC load line. Okay, the first thing we need to do, though, is determine the load resistance we're driving, and normally we'd know what that is, but for this case, let's just assume it's going to be 100 k ohms and go with that. All right, so now we need to determine R prime L, that is the effective external large signal load resistance that the cathode is looking at, and that's going to be RK1 plus RK2 in parallel with RL, and that works out to be 49.2 K in parallel with 100 K, which is about 33 K ohms. All right, and now we can find the endpoints for our AC load line. Let's start with IP sat, and we're going to use the same formulas we did before. That is, IP sat equals IP Q plus VPK Q divided by R prime L. So we've got 2.5 milliamps plus 125 volts divided by 33 k ohms, and that's 2.5 milliamps plus 3.8 milliamps, which is 6.3 milliamps. So there's one endpoint for our AC load line. The second endpoint is VPK cutoff, which is VPK Q plus IP Q times R prime L. So again, we've got 125 volts plus 2.5 milliamps times 33 k ohms, which is 125 volts plus 82.5 volts, which is approximately 208 volts. So there are the endpoints for our AC load line. So let's go up and switch colors here to red, and we'll find these points. 6.3 milliamps. Let's see, that's going to be about right about here. And 208 volts. Let's see, there's 205. That's going to be right about here. And let's connect these up. And here is our AC load line. Now, just like we did previously, we're going to determine our minimum VPK value, which is the intersection of the AC load line with our VGK equals 0 curve, and that's right here. And it looks like it's pretty darn close to 50 volts and 5 milliamps. So our VPK min is about 50 volts, and our IPK max is about 5 milliamps. Okay, IPK max. And now we can find our voltage swing out of this thing. So we're finding these voltage intervals here and here. All right, so our swing from the Q point to the right end of the load line, well, that's going to be 82.5 volts. And on the left-hand side, VPK min is the difference between the Q point and, or I'm sorry, our maximum negative swing is the difference between VPK min and VPK Q, which is about negative 75 volts. All right, so there is our output voltage compliance. We can get a pretty large output signal swing from this, and that's why we use this modified biasing arrangement instead of the original cathode biasing circuit that we looked at on the first page of this presentation. Now, our next step is to do the small signal AC analysis of the amplifier, but before we do that, let's look at this equation for R prime L for a second. I've assumed here that our grid resistor is very, very large compared to RK1 and RK2. Otherwise, I'd have to modify this equation and place RG in parallel with RK2 inside here, and that would make this thing really messy. But remember, normally R sub G is a very large value, around at least 470 k ohms typically, and often 1 megohm. So that's large enough that we can disregard its effect on the AC load resistance external to the amplifier here. All right, so now let's go on over to the next page and we'll do some small signal analysis of this amplifier. Okay, here's our circuit redrawn with all the resistor values we calculated plugged in, and I also put in some values for these coupling capacitors, and they're really much larger than they need to be, but we'll talk about these values a little bit later. All right, now over here on the right hand side, I've redrawn the AC and DC load lines and labeled the pertinent current and voltage values. And finally, over here we've got our small signal AC analysis equations, and I've labeled some resistances over here that will make these equations a little bit simpler to work with. R sub T is the total DC resistance looking out the cathode, RK1 plus RK2, and R prime K is the total small signal cathode resistance. That would be RK1 plus RK2 in parallel with RL and in parallel with the dynamic plate resistance as well. So let's start with our voltage gain equation. This is the same equation that I presented on the very first page of this presentation, except that R prime K is a little bit different because we've got these two resistors added. But in any case, our voltage gain works out to be, if we plug in the numbers, 16.8 divided by 16.8 plus 1, or 17.8, which is a voltage gain of 0.94, and that's pretty good considering the ideal voltage gain is 1, so we're not bad. Okay, let's look at the input resistance here. Now, Rn is equal to the grid resistor times 1 over 1 minus AV. Now, this 1 over 1 minus AV factor comes from the analysis of the resistor that is located effectively in a positive feedback loop. Remember, we've got non-inverting gain from the grid to the cathode, and if we were working from grid to plate, we'd have inverting gain. And as we've seen before, when you have a feedback resistor in the feedback loop from an inverting amplifier, we get a reduction of the feedback resistor. In this case, this acts like a feedback resistor that's in a non-inverting amplifier, so we're going to get a larger value. Now, as long as our gain is less than 1, we're okay here. If our gain was larger than 1, this would actually probably turn this amplifier into an oscillator, and we don't want that. But in any case, this is something that's called bootstrapping, and we'll talk about that in another video. But for right now, let's just plug in the numbers and we'll see what we get here. Rn is equal to Rg 1 megohm times 1 over 1 minus 0.94 is 0.06. So that's going to be 1 meg times 16.7. So our effective input resistance is 16.7 megohms. That's really high, and that's a good thing. This is a buffer. It's supposed to have high input resistance and low output resistance. So now let's go over and look at our output resistance equations. All right, grinding through the Thevenin's analysis of this thing, and a page or so of algebra, we come up with this equation. And an equivalent form here is maybe a little simpler to work with. But if, regardless of which of these we use, if we plug in all the numbers, we get an output resistance of, let's see, what do we come up with? About 305 ohms either way. All right, so we have a fairly low output resistance, and although we're driving a pretty high resistance load this time, we could effectively drive a much smaller resistance because of this. Now, the approximation down here, 1 over GM, is not too bad in this case. If we calculate it using that one, we get a resistance of 323 ohms, which isn't bad. And really, do we need to go to all the trouble of deriving and evaluating these complex equations? I mean, we're not designing surgical robots or rockets for SpaceX. We're designing guitar amplifiers, so maybe this is just a bit excessive. But I do like to show you the real deal equations and show you where they come from. So, it's not necessarily required to use these, but why not? Okay, so there are the small signal parameters for this amplifier, but there's another modification that you'll sometimes see, and that is, instead of taking the output from directly off of the cathode, sometimes the output is taken from this node, and we're going to look at that next. Okay, here's our circuit redrawn with the load connected now to the junction between RK1 and RK2, and this is going to affect both the small signal analysis and large signal analysis. So let's take a look at those equations. Our new R prime L is RK2 in parallel with RL, and the total cathode AC small signal resistance is now R prime L plus RK1 in parallel with the dynamic plate resistance, and both of these equations are different than the previous version, and their effect will be reflected in the first factor of the voltage gain equation here, and the second factor is due to the existence of a voltage divider here consisting of RK1 and the total AC resistance down this way, R prime L. So our overall voltage gain is going to be lower, and depending on the value of RL, it can have a pretty drastic effect on these equations. In this case, it's not going to be too bad because we've got a large load resistor, but it can be pretty significant. All right, our output resistance is now modified, and it's going to be higher than for the previous version of this circuit. And finally, the input resistance is still given by the same equation, but our voltage gain will be different because of the modification to our gain equation. Okay, now coming over to our large signal analysis equations, you can see that I have an R prime L given here. It's not the same as R prime L for the small signal analysis, but I can only come up with so many different names for all these resistances, so I'm just going with R prime L here again. And this equation is different than it would be for the previous circuit. All right, it would have been R prime L equals RK1 plus RK to the quantity in parallel with RL. So it is significantly different, and the difference here will be propagated through all of these other equations. Now, IPSat and VPK cutoff, these are the same formulas that we've used for everything from BJTs and FETs all the way up through vacuum tubes. The difference here is that R prime L is defined differently here. And finally, VO max and VO min are also given by the same equations we've always used, except this time they're scaled by the voltage divider ratio here. And if RL is a low value, that can really have a big effect on these voltages. Now over here, I've got the values we calculated for our original circuit, and if we crunch all the numbers here for the modified circuit, these are the values we come up with. So the voltage gain is a little bit lower. The input resistance is significantly lower, but it's still nice and high. Our output resistance is really pretty high compared to the original circuit, and that's a disadvantage of this one. It's going to tend to have a fairly high output resistance. Our AC load line limits haven't changed too much here. Again, that's because RL is pretty big. And our output voltage maximum and minimum values have decreased a little bit. Again, not too badly because we've got a large load resistor. Now, of course, you know I had to build the circuit and test it, so let's go take a look at that now. This is the original version of the circuit where we coupled the load directly to the cathode, and down in this table I've compiled some of the theoretical and experimental values that I verified. So our IPQ in the experimental circuit came out very close, a little bit less. VPKQ was a little bit on the high side, probably acceptable. Our VGK was reasonably close. Our cathode voltage with respect to ground was a little bit lower, and again that's because our VPK was a little bit higher. And finally, the voltage gain was right on the money. It was 0.94. Here's the scope trace I used to determine that. I had 10 volts peak to peak coming in at 1 kilohertz. We got 9.3853 volts coming out, so that's about 9.4, so our gain is 0.94. Now I moved the output down to the node between RK1 and RK2, and that's shown over here. And of course the DC values didn't change at all, but our voltage gain theoretically dropped to 0.88, and the experimental value again was right on the money at 0.88. I have 10 volts peak to peak coming in. I have 0.8787 coming, 8.787 coming out, so that's a gain of 0.88, and everything works out as we would expect. Now, I said I was going to do a few derivations at the end of the video, and I'm going to, and if you want to stick around for that torture, we'll get there in a second, but first I'd like to leave you guys with a problem to do. This one is using a 12AX7, and we're shooting for basically a similar Q point I did in the previous problem, 125 volts from plate to cathode, but this time we want 0.5 milliamps for IPQ. So just complete the rest of the design, do the DC and AC load lines, calculate all the usual stuff, and now let's go on and do a couple of derivations. Let's start with the derivation of the voltage gain for the basic cathode follower. The actual circuit we're starting with is shown here in the upper left-hand corner of the page, and the first thing we can do is combine RK and RL into a single AC equivalent resistance R prime L. Then I'll replace the triode with its small signal voltage controlled current source model, and we get this equivalent circuit shown here. Now, it's not entirely obvious, but the dynamic plate resistance little rp is directly in parallel with r prime L. So we can combine these two into an equivalent resistance as shown over here, and we'll call that r prime K. And with that circuit reduction done, we'll now write the KVL equation starting here at Vin, where we have 0 equals Vin minus VGK minus Vout. That's shown here. And of course we know that Vout is equal to GM times VGK times R prime K, so we substitute that in. And then we're going to solve for Vin, which gives us this equation, Vin equals VGK plus GM VGK R prime K. And we know that Vout is equal to this current times R prime K. We have this equation. So we divide equation 2 by equation 1, which gives us this ugly looking thing. And we can cancel VGK from each factor as shown down here by factoring it from the denominator, which gives us the final equation shown down here. Next, I want to derive the output resistance for this circuit, so we'll go on over to the next page, and we'll start with the small signal AC model as shown up here. So basically what we're doing here is looking into the output of the amplifier from the perspective of the load resistance. In this case, I'm going to use Thevenin's theorem to determine the output resistance, and in particular, I'm going to use a test voltage source, and we'll determine the resulting current that flows out of that source to determine the Thevenin resistance, V test over I test, which is also the output resistance of the circuit. So we apply the test source and we deactivate any independent sources in the circuit. We only have one, that's Vin, so we replace it with a short circuit, and this is the equivalent that we get. Now remember, we can combine little rp in parallel with rk, so if we do that, we'll come up here, and I'm renaming that resistance r prime k. And I've also moved the grid down so that it's readily apparent that VGK is in parallel with V sub test, but because of the orientation of the voltage sensing arrows, VGK is equal to negative V sub test. And another thing we can note here by inspection, since V sub test is directly across R prime K, the current through R prime K is V test over R prime K. And if we begin to compile some of these equations, the first one I've got is V sub GK equals negative V sub test. And if we do Kirchhoff's current law at the cathode, we find that the test current is equal to V test over R prime K minus GM times VGK. Then we can substitute the first equation into the second one, which gives us I sub test in terms of V sub GK. Now, these are all the pieces we need to put together to determine the output resistance. So remember, RO equals RTH, which is V sub test over I sub test. And we know that V sub test equals negative VGK, that's equation 1. And we also have an equation for I sub test, that's down here, that's equation 3. So when we substitute 1 and 3 into our Thevenin resistance equation, we get this messy looking compound fraction here. Now, to make it a little prettier, I'm just going to cancel out the negative signs, and that gives us this version. Now, we can put the two terms in the denominator over their own common denominator by multiplying the right-hand term by r prime k over r prime k, and that gives us this equation. We combine these two fractions in the denominator, and now we've got a compound fraction that we can do something with. That is, we're going to take the reciprocal of this bottom fraction and multiply it times the top, the numerator, v sub gk, and that gives us this equation. Note we've got VGK in every term, so if we factor that out of the denominator, we can see that it cancels out, and we end up with our final R out equation as shown here. And we can also show that if we just take 1 over GM in parallel with R prime K, we can algebraically manipulate this to show that these two are equivalent to each other. Then finally, because R prime K is often much greater than 1 over GM, and that is R prime K, let me add a prime here, we can usually use this approximation for the output resistance and get very good results. Now, I thought about doing the derivation for the input resistance of the cathode follower with a split cathode resistor, but when I sat down and really worked through it, it was just so long and tedious. There was no way I could avoid solving a bunch of simultaneous equations, and it was really painful. So I'm not going to subject you to that today. Maybe sometime in the future, if I lose my mind, I'll present a video showing that, but for now we'll just let it go, and that's it for today, and I'll see you guys next time around.